realized, our speaker is Tom Collett from Portsmouth, who's an expert on how dark energy is affecting the expansion of the universe. So Tom did his PhD at Cambridge at the IOA. Our speaker is Tom Collett from Portsmouth. 1 second. Who's an expert. Sorry, the YouTube live stream starts and then I hear myself talking back to myself and then I can never keep a train of thought. So yeah, Tom did his PhD in Cambridge and then moved to Portsmouth as a postdoc, a research fellow, picking up a few prizes, a URF, and has recently been awarded an ERC starting grant. And so will then continue at Portsmouth for the foreseeable future and permanently, I think. So that's fantastic. So today, Tom's going to be talking to us about strong gravitational lensing as a cosmological probe. So Tom, again, thank you very much for agreeing to speak to us, and please, whenever you're ready.
Thank you very much, and thank you for having me. It's a pleasure to be invited, and lovely to talk to you. I'm afraid I can't come and see you in person, but hopefully sometime in the near future. So yeah, so I'm going to talk to you about strong lensing, the Hubble constant, testing general relativity, and the cosmological parameters. So there we go. So strong lensing occurs because massive objects warp space-time. What that means is that light traveling past an object like a galaxy or a cluster is deflected. And so if you have a background galaxy, shown here in blue on this schematic, almost perfectly aligned behind a galaxy with respect to us, then you can see multiple images of that same galaxy on either side of the lens. And this is what we see in this example, where we see a blue background galaxy, looks something like this little blue one in the bottom right, if it weren't for the lensing. And then is deformed into this horseshoe-like Einstein ring. Now, these Einstein rings are interesting from a cosmological standpoint because, holding everything else equal, a bigger Einstein ring means a faster expansion rate of the universe. That means the Hubble constant is greater. Now, the Hubble constant is currently a key source of tension in cosmology. Measurements from the cosmic microwave background give a value of about 67.4 plus or minus half a kilometer per second per megaparsec. Similar results come from taking baryon acoustic oscillations or taking BAO measurements to sort of redshift 0.5-ish, and then using the standardizable nature of supernovae to extrapolate down to what the Hubble constant should be today. Whereas measurements from strong lensing, which I'll tell you about in this talk, give a value of about 73 kilometers per second per megaparsec, and values directly measuring the Hubble constant from supernovae, using type 1a supernovae as standard candles, give a similar high value. So these two camps of results can be divided into groups, essentially of the things that measure the Hubble constant directly in the local universe, the cosmic distance ladder, strong lensing, you get a similar result using water masers, versus a lower camp of results that rely on various aspects of early universe physics, be it the sound horizon scale, imprinting on the cosmic microwave background, or imprinting on BAOs. Now, this could be a sign of new physics. Maybe some of those assumptions in the early universe modeling are subtly incorrect. Maybe the extrapolation from redshift 1000 down to redshift 0 is incorrect, i.e. the lambda CDM model is not quite right. Or perhaps it's just systematics. Maybe these error bars are underestimated, and perhaps there's a concordance value somewhere on this plot. And it's hard to know which of these is correct, because ultimately systematics are hard to rule out without having lots of independent measurements. If there were one outlier on here and everything else agreed, you'd be inclined to say that's probably a systematic in one of the measurements. But the fact that things are a bit more complicated than that is at least interesting. So as I said, strong lenses are interesting because a bigger Einstein ring means a higher value of the Hubble constant. But the problem is that a bigger Einstein ring could just as easily mean the lens is more massive. Bigger object warps space-time more, the deflection angles are bigger. And so there's clearly a degeneracy here between the cosmological parameters and the astrophysics of the lens. So this is encapsulated here in this equation at the top for the Einstein radius. It's a function of the mass within the Einstein ring, and it's a function of 3 angular diameter distances. So if you want to learn about cosmology, you need to lift this mass distances degeneracy. And there are 3 ways forward for doing this. And I'll spend a little bit of time telling you about all of them. The first of them is you could get an external tracer of the mass. You could use, say, the velocity dispersion of the stars, how fast the stars are moving within the lensing galaxy, and use that to infer what distances must go into this Einstein radius equation. It turns out that that's quite hard to do, to measure velocity dispersions very well, unless you have a very nearby lens. And at that point, actually, the angular diameter distances become very insensitive to cosmology, and you're left with a great test of GR, whether this Einstein radius really is what's predicted by this equation. And I'll tell you a bit about that later. You could go to a system where you have multiple background sources. You imagine taking the ratio of 2 Einstein radii. You've got the same lensing mass, but you've got different distances. So if you take that ratio, you can learn about cosmology that way. Turns out that's a really sensitive probe of dark energy. Or the most established way of doing cosmology is to use time variable sources. So you see this one in the bottom right, a lensed quasar. When the quasar flickers, you don't see the flickering happening in the images simultaneously. The reason for that, if we look at a schematic, is that light is traveling on different paths, both through the universe and through the lens. So there's a difference in geometrical distance. So the light simply travels further, and given the finite speed of light, that means that it can take longer to arrive. And there's also a GR effect called Shapiro delay, the fact that clocks run slower when they're in deep potential wells. And these 2 effects tend to add up in the same way, such that these images that form close to the center of the lensing galaxy arrive later than the ones further away. So if you have a flashing source, or imagine you have an exploding supernova, you would expect to see this image first and then this image second. So these time delays are proportional to something called the time delay distance. It's a ratio of 3 angular diameter distances. And in our universe, at least for the typical redshifts that we see lenses and sources at, this is predominantly sensitive to the Hubble constant. There's some mild sensitivity to omega matter, the matter density of the universe, and some sensitivity to curvature and to dark energy, but really this is primarily a probe of the Hubble constant. Now, the time delays are proportional to the time delay distance, but to actually measure the time delays themselves is a challenge. So the problem that you've got, particularly with lensed quasars, is that they vary in a sort of unpredictable way. They flicker. They don't vary by huge amounts. You're not talking about magnitudes of variations. You're talking about maybe 0.1, 0.2 magnitudes over the course of a year. And that's for some of the most variable quasars lens quasars that we found. So here is a light curve for 2 images of this particular system. And they've been offset by 119 days. And hopefully you can see roughly that the things all line up with each other. They don't line up perfectly because there's a problem of stellar microlensing. So because quasars are incredibly small and because lensing galaxies have stars in them, it's not at all uncommon for a single star in the lens galaxy to form perfectly or almost perfectly on top of where one of these strongly lensed images are. And that can cause temporary magnification. So you see on this light curve, there's a feature here that isn't really in the light curve below, and that's most likely due to an individual star just crossing over that image A. So this makes measuring the time delays challenging, and indeed historically, this was essentially the main bottleneck for measuring the Hubble constant. If you only measure these light curves for a year or so, then it's almost impossible to disentangle intrinsic variability of the lens quasar from these random microlensing excursions being taken on independently on the two light curves. So historically, people used to get 50 or 100 from strong lenses for the Hubble constant because they just weren't monitoring the lenses getting the time delays measured correctly. Now the Cosmogral collaboration has been monitoring about a dozen lenses for about a decade, getting nightly or every other nightly observations, and that has yielded sort of measurements of time delays that are typically order up to 3 days of uncertainty on them. The typical time delays themselves are 1 to 4 or 5 months, and so that means that we're talking about precisions ranging from sort of 1% uncertainty up to about 5 or 6% uncertainty from measuring the time delays. And these analyses are now well evolved and independently done blindly by multiple groups. So I think it's fair to say that it's unlikely there are systematics coming into this measurement now. However, the time delays are not the time delay distance. They're only proportional to it. So this equation here, I'll try and not give you too many equations in my talk, but this is sort of the key one that explains the relationship between the time delays with the time delay distance and then the geometry of the lensing system. So θ1 and θ2 are the positions on the sky that we see the images, whereas beta is the unlensed image position that we don't know. And so this is just a Pythagoras theorem difference in path length geometrical term. And then these two are telling you the difference in the Shapiro delay, the amount of time dilation that's experienced as you pass through the lens. So to solve for this equation, you basically have to know how the mass is distributed in the lens, because you need to know the lensing potential for these psi terms, and you need to know this beta, the unlensed source position. So what that boils down to, as I said, is knowing how the mass is distributed in the lens. So when we think about a doubly imaged quasar like this one on the left, you've basically got two constraints here: the image, the positions of these two images. You know that they come from a single background object, so that you know that whatever the lens model is, it needs to be able to focus those 2 points. But beyond that, you know very little. And indeed, you can fit almost any mass model and get those 2 points back into a single self-consistent position. And what that means is you can get almost any value of the Hubble constant from a system like this one. And that's why the Holy Cow collaboration and other collaborations looking at time delay lenses have focused on systems like this one on the right. So this is a quadruple imaged quasar. You see the 4 bright points. This occurs because the lens is not perfectly spherical. When you deviate from spherical symmetry, you can get 4 images. And so we know that all 4 of them need to trace back to the same position. But we also see the unlensed host galaxy here. So you see this orange bulge, the bulge of the host galaxy of the quasar, and you see these blue clumps that correspond to knots of star formation. And this is really constraining, because we now know that we need to de-lens all of this into a single astrophysically sensible background host galaxy and get those 4 points of the quasar correct. So the way we do that is through a process called lens modeling. It's a ray tracing or an inverse ray tracing approach. basically you guess a mass model, and then you shoot rays at your image plane, use that mass model that you've guessed to trace them back onto the source plane, and you do that for every pixel in your image, and that lets you build a giant matrix that relates what you see to the parameters of your unknown source. You can invert that matrix, adding some mathematical constraints that allow you to basically infer the correct amount of clumpiness in the source without over or underfitting the data. And that lets you see how well that this particular guess of a mass model can do at reconstructing this image on the left. Some will do well, some will do badly, but the point of that is that you've now got a likelihood function. And so if you have a family of mass models that could all plausibly describe the lens, you can run a sampler, explore the parameter space, find the best fit, and see what range of models is consistent with the data. Now, we've done that for 7 lenses so far. This is the F814W HST image of that lens I was just showing. And you can see that the best fit model shown on the left broadly reconstructs that bulge of the quasar host and gets these star forming knots. And as a bonus, you get a kind of cosmic telescope to look at what the unlensed source would have looked like. And as you can see this bright patch in the middle, which is that bulge, and you can see these knots of star formation that were blue on this color image. Now, the best fit is not particularly interesting, right? We're scientists. We're interested more in uncertainties than absolute values, and so we run MCMCs blindly to see sort of what range of parameters for the Hubble constant can reconstruct this data. We've done this for 7 lenses, blindly for 6 of them. The first one we sort of got used to making the analysis as a community, but on here that's the red PDF. But all of the other lenses on here were blind measurements. And you see that not only do they scatter in a way that is consistent with their error bars, you know, they're not all giving exactly the same value, which you wouldn't expect given the uncertainties on the measurement, but they're equally not some of them giving 50 and some of them giving 90. They're scattering as you expect, consistent with there not being huge systematics between the measurements. This sort of test doesn't rule out systematic shifts that move all of the lenses together, but it does suggest that there are extra sources of that scatter within the individual lenses. And as you see, the central value of this is 73.7 plus or minus 1.5, which is consistent with that cosmic distance ladder measurement from the Shoes collaboration, and is 3 or 4 sigma higher than we get measuring it from the CMB. Now, this is assuming lambda CDM, assuming a fairly broad prior on omega matter. But if we allow the cosmology to relax a little bit, let's say we allow the equation of state of dark energy to vary, so not fix it as a cosmological constant, but let it deviate from -1, then we find that the error bars blow up quite a lot. So if you're willing to get rid of lambda CDM, this is not a truly direct measurement of the Hubble constant. There is some sensitivity to lambda CDM, but that would be exciting, right? If lambda CDM is not the correct model of cosmology, that would be fascinating. So the error bars blow up for W. They similarly blow up if you allow for cosmic curvature. The reason for this is that I'll unpack this slide in a minute. These time delay distances are proportional to this ratio of 3 distances. And so basically you have degeneracies that crop in here from between the cosmological parameters. The leading term is H0, because all of these angular diameter distances are proportional to 1 over H0. but there is some cosmology hiding in here. Now, an alternative way that you can use these samples to learn about the Hubble constant directly is calibrating on unlensed type 1a supernovae. So the fact that these are standardizable candles means that they tell you very precisely that how the luminosity distance grows as a function of redshift. And they don't tell you the absolute value of the Hubble constant because you don't know the absolute magnitude of a type 1a supernova, but they do tell you what the shape of how these luminosity distances grow as a function of redshift. Given that luminosity distances are related to angular diameter distances by this relationship in sort of almost any sane cosmology, what that means is you can plug the supernovae into these time delay distances, and you're left with a measurement of the Hubble constant that depends on nothing other than cosmic curvature. The reason curvature crops up is because you've got these DLSs, which is distances between lens and source, which you can't directly measure with supernovae. You do all of this, and what you get, this is some work from a paper I wrote in 2019. This only uses 4 lenses, but the results are not significantly different for the sample of 7. If you insist that the universe is flat, you draw a line through this omega k equals 0 slice here. You get a high value of the Hubble constant with slightly larger error bars than you get from assuming lambda CDM, but not significantly larger, and certainly not enough to give you confidence that the tension with the CMB can be alleviated. So it doesn't look like this tension is coming from, say, dark energy, or well, it could be curvature, right? You could have a very low value of the Hubble constant if you have a very extreme value of curvature, but really that's inconsistent with what we see in the CMB. So it doesn't look like these uncertainties, this dichotomy between the Hubble constant locally and a high redshift is because we're expanding the universe in the wrong way between redshift 1000 and redshift 0. It looks like lambda CDM is holding up in that regard. So what else can we do for measuring the Hubble constant? Well, before I tell you about sort of the latest progress in this time delay measurement, I'm going to transition off and talk about testing general relativity using stellar dynamics. The reason I'm going to do that is that using these stellar dynamics is going to turn out to be a really interesting systematics test for the Hubble constant measurements that I told you about before. So this equation up here for the Einstein radius is only true if you believe general relativity. So you can write down sort of simple extensions to general relativity that basically change the amount of curvature produced per unit mass. Then with this gamma, which is 1 in GR, you get an equation for the Einstein radius that is given by this equation. Exactly the same as before, just with 1 plus gamma over 2 rather than a 1 going there. Now, these theories such theories of gravity are interesting cosmologically because potentially they can cause acceleration without the need of a dark energy. So if you write down the most general metric of a weakly perturbed Robertson-Walker spacetime, sorry, this is another one of those ugly equations, but basically all you need to know in here, this is your differential line element. You've got your expanding universe scale factor, and you've got 2 potentials in here, one that goes into the time-like part of the metric and one that goes into the space-like part of the metric. Now in GR, they're the same, and the ratio of them is this gamma parameter, but you can have other theories where they're not. Now, they do need to be the same in the solar system because we very precisely measured with things like the light travel time to Saturn when the Earth and the Sun and the Cassini probe were almost perfectly in conjunction. The light feels Shapiro delay as it travels past the Sun. That was measured very precisely and basically recovers the GR prediction. So we know that on solar system scales, things need to be very consistent with GR. These potentials need to be the same, but it's possible that they could vary as a function of scale. And indeed, the reason that one might want to do this, you can have ones that theories that look like this. This is called F of R gravity, that can give an effective equation of state for your expanding universe that looks a bit like a cosmological constant. Now, in practice, a lot of these theories are now severely curtailed by the fact that we observed the binary neutron star, the speed of gravitational waves, to be essentially the same as the speed of light. But that doesn't rule out sort of potential further extensions that could make this still an interesting kind of thing to test. But the fundamental idea of does space-time curve in the way that GR predicts. And so to test this, you need to solve the equations of motion in this space-time. And what you find is that for non-relativistic particles, that their equations of motion are sensitive only to this phi potential, whereas for relativistic particles, they're sensitive to the sum of the two potentials. So if you want to test whether these are the same, you need to find a relativistic tracer and a non-relativistic tracer around the same massive object. Now, this was the test that Eddington wanted to do back in 1919 to see whether the GR prediction that these two potentials exist are the same is correct. In Newtonian gravity, you essentially only have one of these potentials. The other one is not there. And so in Newtonian gravity, the prediction for gamma is 0. So Eddington wanted to test this, looking at basically the deflection of light around the sun. So Eddington does, as all good observational astronomers do, he books a holiday off to some tropical paradise to look at the sky. Now, in this case, it was not a trip to Hawaii, but to the island of Principe off the coast of Africa. The reason being that was where the 1919 solar eclipse was passing over. And so by looking at the locations of stars 6 months earlier and comparing them to exactly where they appear close to the solar limb during the eclipse, you can see what the deflections are. And indeed, he reported a value of 1.1 with an error bar at the time of 0.1, totally consistent with the GR prediction, and very much, even after accounting for systematic errors on the challenge of making the measurement when you're observing once in the dark when it's cold and once in the day when it's hot, and so things have expanded. The systematics are still small enough that indeed GR held up. Einstein becomes famous, and you all know the story from your public talks. So I wanted to make a very similar measurement, but instead of looking at things on solar system scales, looking at astrophysical scales. So this is a very nearby, at least for a cosmologist like me looking at strong lensing, a very nearby elliptical galaxy, E325, phone number. It's a redshift 0.035, which is such a low redshift that you're almost better off talking in terms of distance. So it's about 140 co-moving megaparsecs away. And the crazy thing is that this galaxy is actually a gravitational lens. You wouldn't realize it from the Hubble imaging directly, but if you fit a light profile and subtract off, then what you see buried deep in there are this blue arc system, which is a strongly lensed source at redshift 2.1. The reason that you can get lensing like this is that elliptical galaxies are essentially isothermal. And so it doesn't matter what distance you put them away from us, because the density profile gets incredibly steep at the center, you can still get lensing, even for very nearby massive objects. It's just a question of the alignment. And so here you've got an Einstein ring with an Einstein radius of about 2 arc seconds. It's close enough, 100 and odd megaparsecs away, that you can go out and actually measure how fast the stars are moving very precisely. So this is what we did with MUSE on the VLT. This is the velocity dispersion field for this galaxy. It's about 400 kilometers per second in the very central regions, and then falling off to something more like 270, 280 kilometers per second far out. And the cool thing about this is that you've now got a completely independent tracer of the mass distribution. You know how fast the stars are moving, you know how Kepler's laws work. So if you can make some reasonable assumptions about the typical orbits of the stars, then you can infer what the mass distribution must be. And the really nice thing about this is just a rebinning of that kinematic data and zooming on into the center, is that compared to the lensing, it has totally different degeneracies. So lensing is very much a two-dimensional effect. You're sensitive to the cylinder of mass that's within the Einstein ring. Whereas the kinematics is a 3D thing. It's sensitive to the distance from the stars from the center of mass of the lensing galaxy. And so that's really cool because whilst there are degeneracies in both of these measurements, they don't each suffer from the same ones. So the most famous degeneracy in lensing is the mass seat degeneracy. I'm going to talk a lot about this in the final third of my talk, where basically if you rescale your mass profile but put and add on a sheet of mass, you can leave all of the lensing observables the same. But if you do that to the kinematics, it looks totally different. And so by putting these together, you can break degeneracies and get a really precise constraint both on the mass profile of the lens and hopefully, as we'll see, a test of GR. So that's indeed what I did, taking a single self-consistent model for the mass and simultaneously reconstructing both the data sets. Here's the lensing, the data and the model. You see the residual gets down very close to Gaussian random noise. There's a couple of features in here that are actually star-forming knots in this region that are so highly magnified that they're only about 100 parsecs across, that numerically the resolution of the code struggles. Most of this source, this clump up here is only doubly imaged. The way lensing works is you get these lines of infinite magnification, which when you cross them, you get two more images pop out. So this image, this part of the source here, well, in fact, all of the source makes up this image here and this image here. But this arc system, which is actually two merging images, is entirely composed of this tiny little clump, which is very highly magnified. And that really greatly constrains the lens model, because if you change the lens model ever so slightly, then you change the bits that are highly magnified and you get something that looks very different. Now, because you don't know the unlensed source position, there are still some degeneracies. But if you imagine a model that changes the way that the caustic passes through the source, goes at a different angle, you get something very different. So this is a really not only unique system because it's so close, but it's unique because you've got this this clumpy feature that's very close to the line of infinite magnification. Similarly, here's the kinematics data, and the model and the residual again gets down pretty much to the uncertainty on the measurement. So we're all happy, right? We can simultaneously fit both data sets, leaving GR or that amount of curvature produced per unit mass free, and see what we get for GR. But first, let me tell you what the mass model is that simultaneously reconstructs both of these data sets. So to reconstruct both of these data sets, you cannot add a constant mass to light ratio for the light and embed it within an NFW-like dark matter halo. So the dark matter halos that come out of large-scale cosmological simulations have density profiles going as 1/r in the very center. And naively, you would expect that the stars the baryonic mass follows where the stars are. So naively, you would expect to just have some constant of normalization that tells you how much mass to add to each of the photons, and then you would just embed that within an NFW halo. The reality is that you can't possibly fit this data with such a simple model. Intriguingly, because both lensing and dynamics are sensitive only to the total mass, you can't distinguish between stars and baryons. So I can give you two alternative models that reconstruct the data, and this is, I think, astrophysically interesting from both sides. One is you can have a very steep increase in the mass to light ratio in the central kiloparsec of the lens. This is shown here. Sorry, that's a typo. That should be the stellar mass to light ratio, not the total mass to light ratio. So rising from a Milky Way-like IMF initial mass function at very large radius, and then becoming super saltpeter, far more mass per unit light in the central kiloparsec than you would expect from even a saltpeter-like stellar initial mass function. So that's one model that fits the data. An alternative model is to fix the mass to light ratio, and then you get back to something close to a Milky Way-like IMF. But that comes at the cost of having to allow your dark matter to really deviate wildly from NFW in the central region. So you need something that is rising, that where the density is increasing by almost 1/r to the r to the minus 3. And that is really an insane amount of contraction. You need some baryonic physics process that can really cause all of the dark matter to come into the very central regions, which again is some sign of interesting astrophysics. So back to the GR test, we can marginalize over these two models, and indeed other models that are completely agnostic about the distribution, whether you put it in stars or dark matter. And this is what we find. Taking just the statistical uncertainties, shown in green, the error just on the modeling alone, you get a value that's pretty much consistent with GR, but with very small error bars. There's a bit of extra scatter coming from that, what we assume, this is shown in red, whether you have your NFW plus a stellar mass to light gradient, or if you want something else. There's a bit of uncertainty coming in from the cosmological parameters, but the primary uncertainty, and that's what gives you this final result of gamma of 0.97 plus or minus 0.09, comes from the actual difficulty of measuring stellar kinematics in the first place. It's really hard to measure whether the width of a line, absorption line that we see is due to the motions of the stars or the intrinsic broadening from the atmospheres of the absorption in the spectra. So consistent with GR and a precise measurement compared to what was out there beforehand. Now, the reason I wanted to tell you this, I hope the GR test was interesting, was that it is also a really nice way of breaking this mass sheet degeneracy. So coming back and looking at the systematics in the Hubble constant measurement from the time delays. So the mass sheet degeneracy, as I said, is a rescaling that lets you change your mass model and leave all of the observables, at least in a static lens, exactly the same, except it changes the time delays, which is the thing that we use to measure the Hubble constant. So if you have a mass sheet degeneracy that you haven't broken, you're not going to measure the Hubble constant correctly. And the absolute magnifications. So if you had a standard candle or a standard ruler lensed, you would be able to break the mass sheet degeneracy that way. You can't use relative magnifications; they all transform in just the right way. So you really need a standard candle to lift this. And the reason this is a problem for the measurement of the Hubble constant is that these mass sheet degeneracies, when you account for all of that messy astrophysics that I touched on before, all look reasonably like physically plausible galaxies. So this is one example, taking a composite model. You've got an NFW halo here in the dashed line for the dark matter, and then a de Vaucouleurs profile for the stars. And the green model, the green lines on here are a true NFW plus de Vaucouleurs, whereas the red, orange, and blue are transformations, mass sheet transformations away from this. That if they were the true model and you'd fit with the NFW plus de Vaucouleurs, you would have got the Hubble constant wrong by 10 or even 20%. And when you look at these profiles, astrophysically, this is density versus radius, they look pretty reasonable. You know, by eye, I can't look at that and tell you, oh, the green one's definitely right and the red one couldn't possibly be. You know, so we need to break these degeneracies if we're to precisely measure the Hubble constant. So the first thing we did, and this is work by Martin Mion, a PhD student at EPFL, was to take the TD Cosmo and Holy Cow lens samples, and instead of modeling them with the mass model families that we'd been using before, we were using both power law profiles and this stars plus NFW composite, but then we just averaged them. We just said, well, we don't know which of these models is most appropriate, we'll just average them. But what Martin did was split them and see if we got different answers depending on the model that we chose. And you see that they're consistent, right? This one only shows the 6 lenses, it's slightly older. But essentially none of the individual measurements move by more than half a sigma. And so this is an indication that there's not really any evidence here for these models being a long way from the truth. But there are still possibilities that they're all systematically varying. You know, if every one of these models was more like the red one than the green one, then you maybe wouldn't expect that to be picked up in a plot like this. What you would expect to see it is in the kinematics, in the motion of the stars, looking at the velocity dispersions. You know, as I said before, the dynamics are this 3-dimensional effect, and so they really do care about a mass sheet. If you add that in, you'll get totally different kinematics. So this is in the top panel here shows the expected velocity dispersion as a function of this lambda parameter. The sort of here is getting the Hubble constant wrong by 20% in one direction, and here is 20% in the other direction. And you see it corresponds to huge shifts in the velocity dispersion, 240 to 290. So if you can measure velocity dispersions well, then it's pretty easy to just break this mass sheet degeneracy, and you're fine. So you go to the VLT, like I talked to you about before. You get your fancy data set, and you measure the Hubble constant. Except you can't, and the reason for that is that the bulk of the lenses used in the time delay cosmology sample are higher redshift. And you've got these annoying things called quasars. And these quasars have really bright booming emission lines. And what that means is that actually measuring velocity dispersions is really hard. And so instead of having the data like this, you get data like this, a single aperture, noisy spectrum that is pretty hard to robustly and accurately measure velocity dispersions for. And it's essentially impossible to do anything in 2 dimensions. So nevertheless, we can do this. We can use this to measure the Hubble constant and throw away the mass models essentially entirely, just use what the dynamics tells us. But the problem is, because we've only got those single aperture measurements, we have a degeneracy again between the Hubble constant and the anisotropy of the orbits of the stars. So this is the question of whether you've got most of your stars moving around in circles or moving in and out on radial orbits. So with only a single aperture measurement and only a handful of lenses, this is what you get for the 7 TD Cosmo lenses shown in purple. The Hubble constant might be 60, it might be 80, not really precision cosmology. What you can do is you can go to other lenses and use them as priors, systems where you've got very much better data and just ultimately way more data to learn about the range of plausible mass sheet parameters. You can't obviously get the Hubble constant because there's nothing time variable, but that doesn't stop you doing a great lens model and learning about what the mass sheet is from the dynamics. And And indeed, you can go to lenses where we have got VLT IFU data and where we can learn about the stellar anisotropy and use that as a prior. And so that's what we did recently in a paper by Simon Birra, where we combined with 9 lenses where we had IFU data. That's shown in blue, where we're just using the anisotropy learned from the IFU data as a prior. Doesn't change the Hubble constant very much compared, sorry, that's in pink, doesn't change the Hubble constant very much compared to the blue. Or you can use the full ensemble of SLAC's lenses. There's 33 of them in this analysis, and they just have the single aperture velocity dispersions, and use them as a prior to give you the sort of typical mass sheet degeneracy parameter. And if you use that, you get a lower value of the Hubble constant. You're back to that CMB preferred value of about 67 with an error bar about 4 kilometers per second per megaparsec. You can combine both data sets, the anisotropy and the density profile priors, and you basically get smaller error bars and the same low value. So we're in a sort of a difficult position here, right? Because I've now got 4 values of the Hubble constant from one strong lensing time delay cosmology collaboration. And whilst we did the original analysis I showed you blindly, and indeed we did all of this analysis blindly, we've now got 4 answers, and choosing them requires us to be a little unblind. Now, from here on, I'll tell you my personal views rather than sort of TD Cosmo collaboration official ones. But my view is that this assumption that time delay cosmology lenses and the non-time delay lenses that come from SLACs are the same is probably not right. And the reason for that is that they've got very complicated selection functions. So lenses in SLACs are found like this. You have shown in dashed here the SDSS fiber, and in solid is a schematic of what a lensed arc system might look like. You collect all of the photons that fall in the fiber, accounting for blurring by the PSF, and you discard anything that's not in the fiber. So in this case, you get this light, and if you get enough light from this background source and it has bright enough emission lines, you find it, you identify it, and it comes in your SDSS SLAC sample. If you make the Einstein radius just a little bit bigger in this example, none of the photons fall in to the fiber. You're highly unlikely, even with blurring from the PSF, to get enough photons to detect the emission line, so you're not in the sample. So there's clearly a degeneracy here in the, there's clearly a selection function here that biases you somewhat about the mass profile of the lenses. Similarly, and here's some work I did a couple of years ago with Steve Cunnington, there's a selection function in the time delay sample. So the fact is we're only able to monitor systems that have multiple bright images. We're focusing on quads that are separated by enough that they're easily resolved. And so what that means, so this plot here shows the density profile of the lens. Black is the input population, the sort of ensemble typical galaxy in the universe, whereas red is the type of thing we think that we're likely to be observing in TD Cosmo. So there's quite a big selection function between the black and the red in terms of the typical density profile as well. So my personal view is that of all of these values of the Hubble constant that have come from time delay cosmology, you can pick the ones where we assume we know the models of the lenses very well. You can have the kinematics only constraints from just the TD Cosmo ones. You can assume that we know the anisotropy fairly well from IFUs, or we can assume the density profile is similar. My personal view is that you should really treat these bottom 2 with a severe grain of salt. They're highly unlikely that the SDSS SLACs lenses are the same as the TD Cosmo ones. Yes, these give you bigger error bars, but they're much more cautious and much more likely to be representative of what we can do from kinematics only. The good news is that we're not that far away from being able to do significantly better and getting down to the sort of precision cosmology, again, that you need to be able to lift that degeneracy between the low and the high value of the Hubble constant. This is essentially where we're at the moment with this unresolved velocity dispersion data. If we can get JWST data, IFU data for the 7 lenses, we get down quite quickly to 3.5% on the Hubble constant without ever having to use any data from SLACs. And excitingly, with 40 lenses, which is really quite trivial for LSST. I don't think I'm going to have time to tell you much about LSST, but we expect to be seeing hundreds of lensed quasars and hundreds of lensed supernovae as well. So even with 40, as long as we can get AO-assisted IFU data or better on the ELT, we can quickly get down to 2% again, which would be, if we get the local supernova result, a 4 sigma tension with lambda CDM, with the Planck value from lambda CDM. So I'm going to wrap up here and just sort of excite you a little bit about the future. The future for this is LSST and Euclid, and these are fantastic survey instruments because they have exquisite resolution and depth, particularly for LSST, compared to anything we've done before. This is sort of a toy lens observed through DES, LSST's best single epoch image, and Euclid. And you can see this one's very hard to resolve, whereas these two are pretty obviously lenses. The important thing about resolution and depth is that when you build a theoretical model for what the Einstein radius distributions of all lenses are in the universe, not just the ones we've discovered, you get an Einstein radius distribution that peaks way, way lower, and this is in log space, than where we've ever probed before. And so running a full simulation of what's likely to be there and modeling selection functions, what we find is that Euclid and LSST should both discover about 100,000 lenses, compared to the few hundred that we know of today. That will include a sample of lens supernovae, where we can use the fact they're standardizable to break the mass sheet degeneracy. I'll skip over this, but basically the summary is that we can do standardization well enough, despite the presence of microlensing, to get a 0.5% measurement of the Hubble constant with the full LSST 10-year sample. And there'll be a sample of compound lenses, systems where you've got 2 rings at different redshifts. Indeed, one of the TD Cosmos lenses is already like this, where the presence of an extra source at a different redshift can also break the mass sheet degeneracy. So that's my summary. The Hubble tension is interesting. Right now, the measurements from strong lensing and the Hubble constant are a little bit up in the air. I personally would say you're best with this pink and blue one, but that does mean quite big error bars. And interestingly, space-time curves, as you would expect from GR, over kiloparsec scales. Thank you.
Tom, thank you very much. That was great. Round of applause is always hard virtually, but I can see some emojis going off in the chat. So there's a lot of really interesting astrophysics there, which I imagine will spark quite a few questions. So who would like to go first? Let's bring up the, I can see. Tessa, got your hand up. Yeah, sorry, couldn't see you.
That's all right, that's right. Thanks, Tom, that was a really, really lovely talk. I didn't quite follow, so maybe you can just reiterate for me. When you were talking about the SLAC sample, and you explained nicely why it is that there's a bit of a selection function going on there that is sort of biasing that. I didn't quite follow the next step as to how that results in the lower H0 parameter.
So we haven't done an analysis that explicitly connects those two facts, but I think so. The assumption that's going on in this orange result here is that the density profiles of SLAC's lenses is the same as the density profile of the TD Cosmo lenses. And I think, given the presence of these two complicated selection functions, you know, if you had a denser concentration of mass in a SLACS lens, you'd make the Einstein radius bigger, and so you'd fall out of the SLACS sample. You know, something like that means that really this assumption that's gone into this orange one it really needs quantifying before I would trust that at any meaningful level. I think it's the jury's entirely out as to whether that is the reason that these two differ. It's also perfectly possible that it's just statistical noise, right? If both of these two measurements are consistent, it could be truth that actually these two models that we used for the first lot of lenses were just not a good description of the astrophysics of lenses. And that's plausible.
Okay, all right. So so I'm getting that there are unproven but plausible ways in which the profile actually directly translates into an H0 biasing.
Yeah, the profile is the key thing. That, you know, it's that thing from the beginning. You know, you need to know how the mass is distributed to know to know the unlensed source position and those Shapiro delays.
Yeah, so I actually meant the SLACS profile that you're selecting. Yeah.
Sure.
Okay. Okay. All right. Thanks for that, Tom. Cheers.
Anyone else with a question?
Yeah, I guess another quick question or another question. I mean, so the SLACS, if I'm understanding rightly, the SLACS ones are completely selected because there's another emission line right in the spectrum at a different redshift from the galaxy. Yeah, so it's basically a spectrum with two redshifts in it. Yeah. So is there another sample of lenses that's kind of, you know, selected from imaging or something that you could use as a cross check?
Yes, so there are
various samples.
There are indeed imaging selected samples. They're selected in completely the opposite way, in that because we've been mostly finding them with arc-second type seeing in things like DES, you have to have a really big Einstein radius to be resolvable as an Einstein ring. Yeah. Now, the problem is that we haven't got a good sample of velocity dispersions for those, and so there's certainly work being done in that direction to try and see. I mean, it'd be a smoking gun if those samples pulled you up over here, that you're looking at selection function effects, but we haven't done that yet.
Thank you.
Anyone else?
I'll chip in with another one if I may.
Yeah, sure. Yeah.
So it was obvious that I was going to ask about the GR tests. So the gamma function that you used, we in a cosmological context would nearly always make that a function of redshift and possibly even of length scale, but let's not worry about the latter. You did at one point explain sort of huge difficulties in obtaining, I think it was the velocity data at higher redshifts. But does that completely rule out any possibility of repeating your really nice analysis for this one system at a higher redshift?
It makes it harder, but this was done with Muse before they put the IFU data on, before the adaptive optics was added. So we have been able to get a bunch of lenses. My graduate students working at this on this at the moment. We've got 10 samples out to sort of redshift 0.1, and one lens, this lens here, is at redshift 0.2, and we integrated for 7 hours on this one because it's got two sources. The reason this is interesting, obviously, you've got way better constraints on the mass profile. In fact, we actually found a third source that's only visible in Lyman alpha at redshift 6, but that's a by the by. But the neat thing about this is that we also get emission line velocity dispersions for this first galaxy. So we haven't finished the analysis. We're a long way from finished, but we'll actually be able to learn about a much lower mass scale object at redshift 0.6. And the problem with strong lenses is they're all in these overdense environments locally, whereas the sources are not selected to be. So it gives you a different flavor for the types of environments. You know, if you talk about these screening models, it's most likely in an underdense region of the universe rather than overdense like the main lenses are. So that we'll get out to redshift 0.2 mostly will get something from this at redshift 0.6, but don't expect quite the same level of precision.
Okay. You said the background galaxy, or galaxies plural, are not selected to be in underdense environments, which I completely understand. But the one that you would really care about having a screening effect going on would be the lens itself, right? So if that's always in a dense environment.
So the thing you have to remember is that both of these are lenses, right? It's just that this one is tiny, and so normally, the Einstein radius of this galaxy is like 0.15 arc seconds. So even with Hubble, you basically would never have realized it. If you had two sources aligned, you probably never would have noticed. But because you've got that boosting effect of the primary lens, you can see just the perturbativeness of this foreground one. So it really does, you really are going to be sensitive to variations from GR in this weird little galaxy at redshift 0.6.
Okay. All right, well, we'll look out for the results at 0.2 then. That would be, or 0.6, that would be great. Thanks.
I'll send my PhD student back to work.
Great.
Cool. Are there any final question for Tom?
Can I go for one?
Yeah, great. Yep.
Hey, Tom. Thanks for the talk. It was really good. So I think you mentioned a bit about how it can be good to look at strongly lensed standardizable candles. Is there any sort of future prospect for looking at strongly lensed standard sirens?
Yes. Yes. So I had a whole nother version of this talk with half an hour of talks about lens gravitational waves. So I can talk for this for a while if you want. But the summary is, we won't expect to see more than order 1 lens binary black hole in LIGO, and that will not have an electromagnetic counterpart. We will expect to see with Einstein telescope in the 2030s, order 1 per week lens binary neutron star. So there's a lot of scope there for lensed standard sirens. The exciting thing is that because the standard sirens are instantaneous, essentially, you get perfect time delays. And because the wavelength is longer than the characteristic Einstein radius of an individual star, you get wave optics rather than geometrical optics. So there's no sensitivity to the small scale graininess of the lens, which is where the lens supernovae will struggle. So it's a really exciting thing, but it's a little bit far away.
Cool, thanks for that.
Okay, so I suggest we thank Tom again for a fantastic talk and a great series of questions and answers. So that concludes the formal part of the seminar. But as usual, we kind of stick around for kind of informal sort of social discussion. And Tom, as I said, you're very welcome to highly encouraged to stay